Hello, my name is Jamie Tucker-Foltz from Harvard University, and this is joint work with Gerdus, Benade, and Ariel Procaccia. This is the online version of our EC 2023 conference presentation. The full version of the paper is available on arXiv. Our paper aims to study political redistricting from the perspective of fair division. We introduce a new cake-cutting inspired model of the problem and prove that a fairness criterion known as the geometric target is always feasible in this model. We also empirically evaluate the feasibility of this criterion using real election data. Let me begin by just a brief introduction of how political redistricting works in the United States. The Constitution says that every 10 years we have to take a census that determines the number of seats in the House of Representatives that each state is allotted. But it's completely left up to the states how they want to fill those seats. And so what states do in practice after each decennial census is they divide the state up into geographic regions called districts, where each district will elect a single representative come election time. And so because it's predictable how people are going to vote, you can use the line drawing to manipulate the amount of seats you win in the legislature. And this is known as gerrymandering. Now, in this little hypothetical toy example, I'm plotting the same state and the same political leanings across the state, but three different redistricting plans. And each one of them gives a different balance of power between the blue party and the red party. So this is known as gerrymandering. The term comes from an election in 1812 in Massachusetts, when Governor Elbridge Gerry, hard G, drew this redistricting plan to advantage his party. And one of the byproducts of gerrymandering is they often have to create really bizarrely shaped districts. And so this was a political cartoon making fun of one of these districts, saying it looked like a winged salamander or a Gerrymander, as this political cartoonist put it. And I like to put this other picture side by side as a modern day contrast because it looks quite similar. In fact, this is a modern day gerrymander from a 2016 election in North Carolina, and this was ultimately thrown out by a court as disadvantaging Black voters in the state. So gerrymandering is a problem. What do we do about it? We might think the optimal way to handle this redistricting problem is to use some sort of a fair, neutral process where we feed in the data about how voters are predicted to vote, and the population data, the geographic data, etc., into some big algorithm, and it spits out a fair outcome that is provably fair. And this is the dream of how we could have a neutral process to do redistricting, but it raises many questions. In particular, what is fair? This is a very tough thing to define. You have many different valid viewpoints on what should be the definition of fairness. Does fairness come at a price? If we're trying to just make fair redistricting plans, does it require really snaky districts or districts that split up communities of interest or other desiderata that we have? What are we sacrificing by enforcing our definition of fairness? Another question is over where does this data come from? The algorithm might be fair, but if you feed it data that's been manipulated or that, say, one party claims has been manipulated, then how do you guarantee that you're actually getting a fair outcome? This could be a thorny political issue. And finally, how do we do this in a computationally efficient manner? Of course, that's always the problem that should be in the back of our minds. And so we want to study this from a theoretical perspective. So we develop a model of the redistricting problem in using the methodology of fair division. And we immediately run into some issues of how to model this problem. And the first one is that the fully realistic model is very intractable to work with. In the fully realistic model, what this problem actually is at a fundamental level is we have these indivisible geographic units, which may be census blocks, precincts, counties, with a variety of rules about how we are supposed to preserve counties, etc. And you have to, but ultimately at the end of the day, it's a graph partitioning problem where we have to partition a graph into connected subgraphs of equal population weight. But from a theoretical perspective, there's very little that can be said about it. It's very dependent on the graph structure, and it's just hard to prove any sort of guarantee about a redistricting process in this model. So prior works on theoretical fair division frameworks for redistricting have instead focused on kind of the polar opposite end, which is known as the geometry-free model. And in this model, there's no constraints at all. You essentially have a certain mass of voters for each party, and you get to place them in buckets that have to be equal population. And you know exactly how everyone's going to vote, And so it's really just like placing voters in buckets and then seeing who has a majority. And this is clean, admits some nice mechanisms that give you fairness and admits some nice theorems, but it, of course, is wildly unrealistic. And so we want to bridge this gap between these two extremes. As I said, another problem we run into is how do we define fair? And just to give you an example of why this is a difficult problem, is the most natural thing you might immediately think of is proportionality, which says that if we look at the number of seats that a given party, say the Republican Party in the state of Massachusetts, gets in the House of Representatives, that should be proportional to its statewide support. Well, I'm showing you a picture of Massachusetts for a specific reason, which is that Massachusetts has nine seats in the House of Representatives. And based on the last census, they had roughly about a third of the support statewide. So they should get about 3 districts. But in fact, it's not possible to draw even a single district that complies with all the legal requirements of Massachusetts that gives the Republicans a majority in that district. And that's because the Republicans are so uniformly spread out throughout the state. It might look from this picture that it is possible, but keep in mind that these are not weighted by population. Some of these Republican areas are much smaller population. So proportionality is not a feasible criterion, so we can't enforce it as a rule when designing a redistricting algorithm or process. So what do? In our paper, we introduce a new model bridging this realism tractability gap that incorporates some realistic constraints, but still is simple enough that we can analyze it theoretically. We prove that while proportionality is not feasible in our model, as it's not in reality, a different notion known as the geometric target, which I'll explain shortly, is always feasible. And we prove this via a sort of cut and choose protocol akin to some other results in the fair division literature. Finally, we show via experiments on real election data that this geometric target notion is feasible in practice as well as in theory. Okay, so diving right in, here's our model. It's called the state cutting model. And it's if you're familiar with the cake cutting model, we're trying to use a lot of the same semantics to talk about things here. So the state we can capture via some unit interval between 0 and 1, and we assume without loss of generality that population is uniformly spread out around the state. Okay, so we have these measurable density functions, Fij, defining the support of party J according to party I. So in this little plot on the right, on the x-axis is the state, and on the y-axis is the density of support for some party. So for example, at 0.5, according to the blue party, that's according to the blue party has 60% of the support in that region of the state. And according to the red party, they have 40% of support in the region of that state. So I'm plotting what the blue party thinks they have and what the red party thinks they have. And so you notice that there's can be 2 different views of reality here. And this is actually a key feature of our model, and I'll justify it in a moment, is that parties can disagree over where voters are. And so in this little toy running example, on the left half of the state, they just happen to agree because they're inverses of each other reflected across the line 0.5. On the right half of the state, they happen to disagree about where voters are distributed. And the reason we allow this in our model is the same reason we allow people to have different valuations in the cake cutting model. We want to design a protocol or a fairness axiom or algorithm, whatever you want to call it, whereby if a party comes and says, this is how I believe reality looks like, then we should guarantee them a fair outcome with respect to that data that they supplied, regardless of the data that the other party supplied. So redistricting is, as you might imagine in this model, partitioning the state into some fixed number m of districts, each of measure 1 over m. And we want to, with these districts, we're allowing to be finite unions of intervals, okay, so not necessarily connected. And in this running example, I'm going to take m to be 10. Okay, so this is one valid district. It's an interval from 0.6 to 0.7. You're allowed to have unions of multiple intervals, but this one happens to be a single interval. And notice that an interesting feature of this disagreement thing is that both parties might think they're going to lose a district. In this case, if you just look at the average value of both density functions, they're less than 1/2 over this interval. So both parties would think they're going to lose this district. Similarly, both parties can think they're going to win a district. This is a district where both parties would think they're the winner. So that's the model. And you can see how it captures this, this realistic constraint that proportionality is not always feasible. In this Massachusetts example, we might capture this by density functions that say never cross the 0.5 line or cross it so infrequently that it's impossible to make a single district where they have a majority. And so that's great. We're capturing that bit of reality. The geometric free model does not. So what do we do that proportionality is not feasible? So we're going to advocate for this alternative fairness criterion known as the geometric target, which states that a party I should receive a number of seats equal to the average between those of its worst and best partitions, the number of seats it would get in each of those alternative scenarios. So in other words, another way to think about it is think about a process where we flip a fair coin, and if it lands heads, then we let the blue party redistrict the whole state. And if it lands tails, we let the red party redistrict the whole state. Then if you think about it, this is fair in a certain sense. It's procedurally fair. It's, you're going to, there's no inherent bias towards one party or the other. But ex post, you're going to have very unfair outcomes. So the geometric target is saying that ex post, we should have the same utility for a party as you would ex ante in this hypothetical system. So it's sort of best of both worlds. This was introduced by Landau and Su in 2014. You can see how this is feasible in the Massachusetts example. The Republicans, their best map gives them 0 seats and their worst map gives them 0 seats. So their target is to get at least 0 seats. Okay, I haven't asked you to do anything impossible. Any map will satisfy this target for the Republicans in Massachusetts. And in the geometry free model, this axiom is equivalent to proportionality, it turns out. So that's why it's kind of nice. It's like when it's impossible to be proportional, it doesn't ask you to do something impossible. But in the geometry free model, where it is possible to be proportional, then they're the same thing. So our main theorem is that in the state cutting model, there always exists a partition satisfying the geometric targets of both parties, each with respect to its own voter distribution functions. And I'll note that this is actually not too hard to prove in the case when the voter distribution functions agree. And we have a separate argument for that case in the paper, which I won't go into. I do want to sketch the more challenging case where the distributions disagree. And so the proof of that a fair partition always exists is via a protocol, similarly to how you prove the existence of, say, envy-free allocation via like the divide and choose protocol in cake cutting. So the first step of the protocol is that each party I places a bid in the form of some union of intervals, and we're going to call that set xi. And so how they're going to do this here, and I'm going to show you on the right one strategy that the party can do that will definitely guarantee their geometric target. And that strategy is to find the maximal part of the largest set possible, such that the average of your density function is a half over that set. Okay, so that's the X set for the blue party, and then this is the X set for the red party. And then we let I be the party with the larger one and let J be the other party. Okay, so whoever has the smaller X set is going to be the divider, and whoever is the largest one is going to be the chooser. So XJ, the one with the smaller X set, in this case the red party, divides party J divides XJ into 2 districts. And then party I chooses one of the districts for J to partition, with party I partitioning the entire rest of the interval. Okay, and in this case, what they're going to do is going to see how that intersects their own partition into equal districts. And I'm not going into the details. You can see the paper for the details and how the optimal strategies look in this game. But in the end, as we reach a point where it's like, okay, here's a choice where as long as party I retains control over just the subset, then they're going to be able to meet their geometric target. So the final partition might look like something like this. This is a partition that could be output by our protocol under optimal play that gives that gives each party a number of seats equal to its geometric target. Please see the paper for more details about how these steps are executed. So that's all I want to say about the theory. The geometric target's always feasible, but is this actually a good fairness axiom in practice? And so what we did is we used we ran some recom Markov chains on some real election data from 2016 to try to empirically estimate whether these geometric targets are actually feasible in real election data. And so what we do is we run a long Markov chain where we take an initial redistricting plan, make a bunch of changes iteratively to it, and then we get this huge ensemble of redistricting plans. We estimate the best and worst partitions for a party by just taking the best and worst observed number of seats. And from that, we can compute what the geometric targets are for each party. And our main finding is that partitions satisfying the geometric targets always exist. And moreover, the price of fairness is low, in the sense that if you take an objective like number of competitive districts, efficiency gap, compactness, and you look at the optimal score that you get through this ensemble versus the optimal score out of all plans that satisfy the geometric target, then this constrained optimum is not too much worse than the original optimum. So, for example, in this table here, the very bottom row is the Polsby-Popper score, which is a measure of compactness. That's about the ratio of perimeter to area. And if you look at, for example, Texas, and then the bottom row of this table, in parentheses is the optimal Polsby-Popper score you could get without a geometric target constraint. And you can see that the other number before the parentheses is the optimal we get that does satisfy the geometric target constraint. And you can see that the constrained optimum is not very much worse. And similar for the other states. Some of the ones that don't have parentheses mean that they're actually the same. So this shows that the geometric target is so readily satisfied that we don't have to actually that we don't have to give up too much to get it. In an attempt to capture the part of our model where we allow the data sets to differ, we also ran some experiments where we consider one party manipulating their data in some structured way. So on the left-hand side, I'm plotting the number of competitive districts. On the right-hand side, I'm plotting the Polsby-Popper score, compactness. In each of the plots, the dashed line at the top is the unconstrained optimum, and the gold bar is the constrained optimum. All the other bars represent the same exact thing in a hypothetical world where we take one of the parties and have it change its election data and then recompute their geometric targets with respect to this new data set and see if we can satisfy the geometric targets of both parties, each with respect to their own data, like we did in the theoretical model. And so the takeaway here is that in all these cases, this is actually one of the worst ones. You can see that our paper for the other data sets, for the other states that we considered, we're not too bad again. So this is just to say there's a low cost of fairness even when the data sets may differ. Well, we just final note that we can we didn't really explicitly consider multi-objective improvements, but here are some plans that satisfy the geometric target and additionally beat the currently enacted plans on all three of these metrics we consider: efficiency gap, competitiveness, and Polsby-Popper score. So that's it for the experiments. The main takeaways from this paper are, firstly, endorsement of the geometric target as a robust minimal standard of fairness. It's so readily feasible both in our theoretical model, sort of gives it a foundation as a good axiom, and our experiments show that it's so easy to satisfy in practice as well, that it could be a good thing on the list of possible fairness criterion to just say, yes, this is a check that this redistricting plan passes because it satisfies the geometric targets of both parties. So that's the first takeaway from this paper, is that this is a good fairness axiom. I'm not saying that means it's fair. I'm saying it's a minimal fairness axiom. If you're not satisfying the geometric target, maybe that's not fair. That's how we would envision this being used, possibly. And secondly, the other contribution of this paper is this new model of political redistricting that really gets around some of the challenges and shortcomings of previous models that have looked at redistricting from the perspective of fair division. And we really feel that this might be useful because it could enable more theoretical investigations of redistricting in something that's not completely intractable like the discrete graph model, and something that's not completely trivial like the geometry-free model. And it enables these sort of arguments we see in fair division, where we think of it as some game and some protocol guaranteeing that a fairness axiom exists. We showed that the geometric target is one such fairness axiom. There always exists redistricting plan satisfying it in this model, but we envision possibly others to follow. Thank you for listening.